first in cricket?
I would actually love to know. So today I'm talking with Neil Saunders. So Neil is introduced to me, and also what I've heard from Neil's own mouth is that he's a pure mathematician, and he's a lecturer here in University of Greenwich, and it's in computing and maths department. So Neil, thank you so much for doing it.
Nice to be here.
Yeah. But I was just saying I would actually be interested to know some sort of a mathematics in cricket. I mean, how do you see it?
Oh, well, that really depends on what you're interested in. Usually with cricketers and maybe with amateur cricketers like myself, it's more statistics than mathematics because we care too much about our batting averages or our bowling averages and how much we need to get an average like this at the end of the season. But if you want to be more serious about it, there's all sorts of fluid dynamics and aerodynamics with swing bowling and rotations on the ball and so on and so forth. And of course, now with technology, you'll have here's a technical term, boffins telling you how far the ball is spinning, how many rotations are on the ball, and so on and so forth. Wow. So there's a lot more mathematics to be had in the broadcast of cricket that there wasn't maybe a decade ago.
Okay, that is actually a very interesting point because, yeah, commentators are now going to be more informed by certain technologies and the calculation. But this, if most of the people, as you can imagine, Pakistan or India, on streets find out that there are certain calculations which they can do and they can improve certain things in their game, they might be running towards the mathematician giving them,
Well, actually, I mean, we can talk about my field, pure mathematics. I'm not a statistician at all, but I had a friend back in Australia who studied and majored in statistics, and I was watching the tennis. I can't remember exactly who was playing, but it was a great match. But they always put those statistics at the end of a set or end of a game. So many first serves in, points won on the first serve, points won at the net, and so on. There's compile statistics and percentages and what have you. I was thrilled and simultaneously jealous to find out that my good friend who majored in statistics was actually sitting courtside typing all of those things into the laptop computer for the live broadcast. Wow. So some people say statistics can be boring. Well, it can be very exciting. Wow. And give you so many opportunities if you're in that if you're an amateur sports lover.
That is fascinating. Who would have thought that I would do a stats degree and then go and do some sort of a badminton or any kind of sports? Okay, so let's maybe, what is pure mathematician? Because generally, I assume that, oh yeah, if you're a mathematician, you're a mathematician. But I guess there is some need to distinguish here. So
yeah, there is some need. I think the distinctions are useful at the start. They're becoming less defined or less set in stone because, of course, the great mathematics, maybe like the great music, happens on the cusps of disciplines. There are disciplines within pure mathematics and applied mathematics, but very, very simply, pure mathematics really is involving abstract thought, really wanting to prove theorems and really get to the heart of why something is true. In a very pure and abstract sense. Whereas applied mathematics, this is a gross generalization, but it might be instructive at the outset, is interested in solving real world problems and using the mathematical theory in particular situations, whether it be engineering, finance, aviation, building and construction. So to that extent, the distinction is useful, but mathematics is still mathematics.
Yeah. So because I've heard more about astrophysics, because of, a lot of media personalities are talking about it, astrophysicists themselves are talking about it. So it could be, somehow, if I compare it, it could be distinguished as theoretical physicist and the physicists who are actually working on CERN, maybe. or so the difference between people who are working on string theory and the people who are working in hadron collider, could that be a little bit of
Possibly. The analogy might be helpful. Like all
yeah,
analogies, they're
yeah,
helpful
yeah,
at the beginning,
yeah,
but
yes,
they can be misleading. But there might be a certain distinction there to be made between theoretical physics and experimental physics.
yeah.
Though, of course, each camp knows what the other side is doing. But physics was an interesting entry into the world of mathematics for me. I remember learning about astrophysics as a Year 12 student back in Australia. You might be able to hear my accent there. And I was just fascinated by the structure of stars and how they emit their radiation and how new atoms are being fused inside the star, which gives rise to the radiation, and then the star will expand to a red giant and then collapse and then maybe explode into a supernova. I found that really interesting. So I went into university thinking I'd like to study physics, and I did study physics. But I remember when I was learning high energy physics in my second year, we were learning about quarks and quasars and leptons and subatomic particles and all those very interesting things. But the lecturer did actually say, if you want to do this subject properly, you're going to need a subject called group theory, which is abstract algebra. It's a pure mathematical subject. It was a subject taught in the mathematics department, not the physics department. So I enrolled myself in that course, and I was really blown away by how beautiful it was. I can't say that I actually understood everything that was going on, but I really just felt like this was something quite beautiful and really something that will be worth my study. And so my interest turned to less physical things and more pure things, and I've stayed there since, though I still have a keen passive observer's interest in physics as well.
I think it's a beautiful way of you talking about pure as an abstract, which is a very interesting concept, because generally when you're talking about a physical material world, somehow that is what most of the people would value more. But it is actually really brilliant, and I think it is interesting if people like yourself are working on abstract concepts and would, emotionally or personally maybe understand it as pure, which is how do you relate to it? Is it something? Am I justifying it? What I'm saying?
There's a philosopher I really like. His name's Daniel Dennett, and he comes up with these lovely little phrases. And one of them is called thinking tools. And while mathematics is a discipline, it's an art, it's a language, it's all those things, it's all just a wonderful thinking tool. It's something that allows us to get over our poor intuitive thinking for the real world in some sense. So if we just take the abstraction thing just for a moment, if you're trying to solve a real world problem, you might look at the specs of the problem, you might look at its intricacies, and you might find a solution. But you might think to yourself, there might be something more general going on here, and there might be some general rule that is always true in problems that are similar. And if you can make that, we'll call it abstraction, but it's just a thought, really. If you can make that distinction, then when you confront a problem that's similar, you can say, actually, that's an instance of this general principle that's going on here. And so we can apply what we've done in the abstract thing to a new problem. And by abstraction, that's all we mean, just extracting a little bit of general principles out of specific things, and then with the hope of applying it somewhere else, or also allowing that piece of abstraction to have a life of its own and express new concepts in that abstract world.
Okay, so how do you actually see your relationship with this discipline, or if you want to call it a discipline? I mean, I guess it's your life, kind of.
My relationship with mathematics is I'm a worker in the great artifice and the great nirvana that it is. It's exploded in the 20th century and before that. There are so many different disciplines and sub-disciplines and disciplines within disciplines in mathematics that it's impossible to know everything. But in my small little field, I have very specific problems that I work on and try to make progress on, and publish and disseminate the work that I do with my colleagues.
So, when you were talking about abstraction in algebra, is that the first thing? I mean, I would love to know a little bit more about the subject itself. And what do you mean when you say a bit of abstraction and you actually fall in love when you were taking that class, and what was that thing and what you learned in that? Because that's an alien language for most of people I've talked to. That's an alien language, and I seriously, I try to read some of your paper, and
They're a
oh
bad place to
my
start.
goodness.
There are some people who could probably read Tolstoy at age 5, but that's like giving War and Peace to a 3-year-old.
Yeah.
Not that I'm comparing myself with Tolstoy.
No, well, you can't. Why not? But it's just your mind somehow resists and it wants to, get away from it. So definitely it's not intuitive, and I guess most of people maybe understand. For some people it might be intuitive. So I would like to know more about this language and abstraction and that algebra which you were talking about, and how certain concepts which you have learned in astrophysics relate to it, and how that journey happened.
Well, maybe we'll give a little exercise for our listeners. Let's try to do a little example. So I mentioned the term group theory. That's essentially a study of symmetries in the abstract. So we'll try to unpack those terms in a little bit.
Oh yes, I'm excited.
Right, here we go. If the listeners have got a pen and paper, maybe let's start. Let's just draw a nice triangle, a nice equilateral triangle, and let's label our triangle with the vertices of our triangle 1, 2, and 3 in any way you like. Well, if I say the triangle has symmetry, that's not going to stretch us too much. We can rotate the triangle, or we can flip the triangle about an axis. And it's not too hard to see that if you rotate the triangle 3 times, you get back to the same triangle that you started with.
Yeah.
And so that rotation, you can rotate it once. So 1 would go to where 2 was, 2 will go to where 3 was, 3 will go where 1 was. We can do that 3 times. We could flip the triangle, so 1 would stay where it is, and 2 and 3 get swapped.
Okay. Yeah.
Then we can do this thing called composing them. We could rotate the triangle and then flip the triangle. And I'll leave the listeners to do that as an exercise. And you can rotate and flip and rotate and do these things in so many ways. If you try to write down all the different configurations of the triangles you'll find there's only 6 of them. Think of all the rotations you can do and all the flips, you'll only get 6 different configurations of the triangle.
Okay.
And we'll call that the set of symmetries of the triangle. Now, let's just put the triangle aside for a second, and let's just have 3 points in a line.
Okay.
Label them 1, 2, 3.
Okay.
Now just ask yourself, how many ways can I align those 3 points in a line? Well, I could have 1 first, 2 second, 3 third, or I could have 2 in the first place, 1 in the second place. I could swap 2 points in the configuration. I could rotate them in a 3 cycle, 1 goes to 2. If you look at all the different ways you can do that, you'll find there's only 6 different ways.
Okay.
And you can rotate the points and swap the points, just like you can rotate the triangle and flip the triangle. And you find that the set of symmetries are actually the same.
Okay.
So the symmetries of a triangle are the same as symmetries on 3 points.
Wow.
In fact, it's called the symmetric group of order 3.
Okay.
So there's an instance that up to symmetry, the triangle is kind of the same as 3 points in space. And so we've taken one object, we've had a look at it, and we've abstracted it to a kind of a different plane, and we've seen that thing turns up in the 3 different ways you can arrange points. A professor of mine back in Sydney says mathematics is nothing other than just giving the same thing a different name.
Okay.
And by extension, giving different things the same name.
Yeah.
And to a certain extent, that's what we do in pure mathematics.
Okay. That was a good exercise for my brain, to be very honest. Although, yes, this is definitely not intuitive.
No, that's why I like the idea of the word thinking tool by Daniel Dennett. And I think it was a student of his who came up with an even better quote, and I've forgotten his name, but it says you can't do much carpentry with your bare hands.
Okay.
You can't do much thinking with your bare brain.
Yeah. Okay. Yeah.
So,
Yeah.
so our brain needs to have these thinking tools, and mathematics is just a wonderful repository of thinking tools that we develop, we refine, we can use in different situations. We can use the same tool for many different situations, and we can also think when these tools don't work or when we need better tools.
Yeah. I think one of the astrophysicists, I forgot if he's a mathematician also, but his name is David Krakauer, Institute of San Jose. And I think he was talking about some research, and I would maybe not recall it exactly how it is, but that how certain capabilities, biological capabilities of humans and maybe our ancestors, chimps, are pretty similar, but the only the difference comes when you add the layer of culture and the society. So I just realized that that's what you might be mentioning when you use math in abstraction, which is actually mediated through storytelling
Yes.
or your imagination, and then you map that imagination, which is just abstract and you have no basis, and put it onto the tool which you are mentioning and exercising.
Sure. I mean, there's a great debate, and I'm not too sure what side I come down on, whether mathematics is created or it's discovered. I don't really want to express a strong opinion about that, but what I will say is mathematics really does allow you to have infinite creativity. Some of the most creative people that I've met have been my fellow colleagues and professors who have just found ingenious ways to solve problems. But the idea of mathematics as a thinking tool and as a thinking tool developed by humans is a very good point, because it is in itself a language that has been shaped and carved and sculpted through years and centuries of discovery and rediscovery and false starts and false starts again until you eventually converge onto an answer.
Yeah, mathematician, surprisingly also, I found most of them happier than other people. And that actually, seriously, actually, so of course they must be solving problems. If they are solving problems, they're solving problems of life also, and the other problems which is happening to themselves somehow. So, and they challenge themselves a lot, so they are a bit more, I would generally say more fulfilled.
Well, I can't speak for all my colleagues.
No.
But,
this is my speculation.
But
Completely.
here at Greenwich, for the last 2 days, we've had the Greenwich Festival of Mathematics, Greenwich Maths Time for school students, and we've had a whole host of wonderful speakers come in, and our student helpers have been fantastic. But there was one speaker who did a brilliant talk on the mathematics of juggling, and he could also juggle 3 to 5 balls in a row. And showed us all the different configurations and combinations by which that can happen. But he said something that was really interesting at the end. He did say that this is fun. It can be fun, but it also can be really hard. Possibly because of our cultural evolution, as Darwin puts it. We bear the lowly stamp of our origin. We have to get over our poor intuitions and so on. So it is hard. It does take some time. And maybe like a creative writer or a poet, I'd say most of the time it's going badly.
Yeah.
Most of the time it's going badly because you don't know how to solve the problem. You have no idea what the answer might be. You've tried and tried and tried, and you just can't do it. But once you do solve the problem, once you make that little brief spark of insight, it's a very, very satisfying feeling, and it's those feelings that really, I won't say make you happy, but do give you a certain sense of contentment.
Yeah. I mean, I have found a lot of mathematicians to be talking about a very specific topic but giving certain very generic advice about life, and I found it very useful and helpful. So somehow maybe that challenge, somehow that constant practice of questioning your intuition and at the same time working with them somehow, because you're pretty much in the blind, might allow you to, practice certain tools of, challenging and transcending whatever you are considering yourself to be. And that might come out as, a bit more positive and less towards the side of where you feel more lost and, have a heavy weight most of the time. That could be but about what you were saying about the discovery, or is it invented? I, I what idea kind of came in my mind, and it would be the perfect place to tell it to you so that you can say what do you think about it. Is that definitely one of the first time I understand why 1 + 1 is 2, and it cannot be 3, or it cannot be any other digit. It was really, it was a whole night. I can't forget that moment where I realized that why 1 + 1 is 2. Because of the certain properties which you observe, and there are no other ways. Otherwise, the formation of the cosmos would not make any sense.
Right.
So I guess what I feel like, that what I'm listening to all the time with the astrophysicists and mathematicians, that maybe this is one of the advanced languages which humans can figure out, which is most closest to somehow laws or rules or habits of cosmos. I mean, the reason why I use habits is because we used to think in laws, and now we realize we haven't figured out. There's a lot of conflicts. So let's call it habits of cosmos.
Sure.
And I that's what I'm thinking at this point.
Well, Galileo in the 17th century described the universe as being written in the language of mathematics. So this idea of mathematics as a language is not new. It goes back. An important thing about languages as well, and this is where analogies are helpful, and maybe make us go down the wrong path in other situations, is yes, it's a language. It has a grammar. It has a syntax. There are syntactical and semantic reasonings you can make in mathematics. But also think about our natural language, the language that we're speaking now, our mother language. Think about how we learnt that language too. We didn't learn the rules of grammar before we started speaking. We started speaking first and then learnt the rules of grammar later. Yeah. And it's that inversion that I think, particularly in mathematics education, is an important one, because it's not necessary. In fact, it's maybe not that desirable for students to know why 1 + 1 is equal to 2. Just the fact that 1 + 1 equals 2, and they can use it for other things. Again, to quote Dennett, I'm sorry, this is a big plug for Daniel Dennett, but he has a nice little tagline in one of his books called "Competence without comprehension." Yeah. Competence without comprehension. Now that's a wonderful little meme, little nugget to keep with you, because that is how, he argues, and I tend to agree with it, that is how cultural evolution has really got going. We've been doing things, we don't really know why we do them, we just do them, they work, and we build on that, and we try some new things, some of them work, some of them don't. The ones that work, we build on that, and we build on that, and so on. I mean, so that's how languages and cultural evolution has worked. Mathematics borrows that to some extent. Now we genuinely do have top-down design, where people think about things, create something, and then go on. But in my field, in mathematics research, even though I am thinking about abstract theorems and trying to prove them, the way by which that I'm doing them is far more on the competence without comprehension side, because I might be trying to prove something, or I might not know what I'm trying to prove. I might just be trying to explain to myself what this phenomena is, and I'm trying a few calculations, and I'm trying a few more, and then I'll try this case over here, and then I might say, oh, that's interesting. What happens if I just vary this slightly? And I have no idea what the answer is. But I am competent at each stage in performing small little calculations, small little gradual bits of information that allow me to piece together a larger picture. Okay. And at the end, and so when you see my published papers, or any published paper of a mathematician, you think it just came out like the way Mozart wrote his music, no scribbles and no erasers. But that's not the case at all. It might look like theorem, proof, example, but I promise you, most of the time it goes the other way around. Example, non-example, mistaken example, then a correct example, then an attempt at a theorem, then attempt at a proof, and then finally you get there. So the idea of mathematics as a language and that competence without comprehension is a really interesting thing to bear in mind. I say that to myself as well as to my students as well, because of course students need to learn the theory and be competent, proficient in mathematics when they come out. But quite a lot of them don't actually realize how important actually doing calculations is to really build up that store of proficiency in understanding what the bigger picture is.
Yeah, so fluency in that kind of language or world. Now, this we have developed that what is the distinction and how beautiful it is if you're thinking in abstraction, because you can get lost. And yeah, we have seen tons of example of people lost in abstraction. But how do you see generally when you are at your peak moments, or maybe even at certain points, how do you seriously see the world sometimes when you are in your flow states and you're really thinking in numbers? And what are you seeing a bit different, because you can speak the language, so there must be a little bit of a difference of perception, I assume.
I wouldn't describe it as a difference in perception, but maybe there is a deep sense of appreciation, a deep sense of the numinous and the transcendent. And I'm not talking anything supernatural or gods and goddesses revealing their wisdom to me.
Yeah.
But there is kind of a real intense beauty that you see once you've kind of made a discovery. It might even be a small discovery. It might even just be something that you didn't understand when you were an undergraduate. And that happens to me quite frequently. There were calculations that I just had no idea what was going on in undergrad, and I finally got it now. It's similar to when you see a beautiful work of art or hear a beautiful piece of music. It's not necessarily a different perception, but it allows you to experience a real sense of the numinous and the transcendent.
Okay, so it just deepens your maybe experience for yourself about different aspects of the thing.
Possibly. I mean, there's a book called Unweaving the Rainbow by Richard Dawkins, actually.
Okay.
And I think he wrote that book, or they gave the title of that book because there was a point where the poet Keats maybe criticized Isaac Newton for explaining the rainbow in terms of how light hits the water drops and how that gives off all the different colors of the spectrum. And I'm no expert on this, but this is an anecdote. And Keats might have said something like, Newton has destroyed the wonder of the rainbow. And maybe in some sense, if you love the idea of a mystery, that we'll never know why this is so, then that might be the case. But when you think about the rainbow that you see is different from the rainbow that I see, but we're still looking at ostensibly the same rainbow, and the rainbow is not there, but it's water drops passing through light. Think about how wonderful and rich that is, and how more enriching and fulfilling knowing that and being able to explain that with the lens of mathematics, with the capabilities that mathematics provides.
Is it John Keats?
Yes, the poet John Keats.
Yeah. I really admire his work. I'm not someone just.
I like John Keats too.
Okay,
I just want to put that out there.
No. I don't think that. I mean, I like him, but I'm not going to defend each and everything he said. I actually think that it is truly more connective when you're describing the truth and the honesty of whatever we know about certain parts of the universe, and it's just letting go of an older description which we might have got used to it, but if we open up to the newer one, and even if they are much harder to understand, but once you understand it, I think I agree with you that it's beautiful what you just described. But I'm just with John Keats, it's he has actually talked a lot about some sort of a science fiction scenarios, and because his name came in, so I'm just going to plug it. His poem called Hyperion. It's actually really interesting, and it has a lot of artificial intelligence and mathematical kind of things. And what impressed me about him that he was actually maybe thinking and interacting somehow with mathematicians, because if he has commented on is who explained it, Galileo? No, who explained
Newton.
Sorry. Oh my goodness. Yeah. So I guess he must be, borrowing those ideas, because that makes sense.
I'm glad you know more about Keats than I do, so I'll have to find some more time to go back to that poem.
This is interesting. So, what else? What are the other phenomena would you like to explain? Because I would love to hear certain other aspects of either your research or maybe dimensions which you have explored to not physically.
I haven't explored. I have explored dimensions, but just for the listeners, I mean the idea of dimension is a very common one in mathematics. We live in 3 dimensions, maybe 4 dimensions, space and time. But in mathematics and in physics as well, you have structures and objects that live in higher dimensions. And one of the great things is mathematics as a thinking tool. Once again, you don't need to be able to visualize these higher dimensions to be able to perform calculations in them. That's a really great feature of mathematics. It allows you to get from one place to the other without it allows you to get from A to D, if you like, without going through B and C. It's a great thinking tool that allows us to overcome our bad intuitions about how things work. So you can define dimensions, you can define all sorts of geometric figures in higher dimensions. When Einstein needed to try to explain or come up with his theory of general relativity, for instance, he needed to develop mathematics, some new mathematics in differential geometry to actually explain it. So there's another instance of how to express something that might be complicated and intricate in the physical sciences. You actually need a language that captures all of that complexity and nuance, and that happened to be mathematics. But I can't remember who else said this. I'm quoting a lot of people who I can't remember who the quote comes from, but these objects that live in higher dimensions, if we could only visualize them, if we actually see what they look like, they would be in every art gallery, in every museum. And in fact, a few years ago, I was in Barcelona in the famous Sagrada Familia of Gaudí.
Okay.
And it was just a wonderful exhibition of some projective geometry, which is something that turns up very much in my work. And just to not bore our listeners too much, but projective geometry is a really fascinating area of geometry. The best way I can explain it is if you stand on a long street, or maybe a long stretch of railway track, and you look at the railways, just make sure a train's not coming by when you do this. It looks like, obviously, the railway tracks are parallel. They quite obviously are parallel. But as you look way out into the distance, they're converging.
Yeah.
And it looks like they do meet. They do meet at some point far, far off. And let's just call that the point of infinity.
Okay.
Well, projective geometry asserts that these two parallel lines do actually meet at what is called the point of infinity. And you can develop a whole system of geometry and topology and functional analyses on these things called projective spaces. And this might be a wonderful thing to do, very hard to visualize, but it's actually very, very useful in proving mathematical theorems and explaining phenomena that turn up in physics and curvatures of spaces and manifolds and et cetera and so forth. So it's very hard to visualize. It's one of the death traps of postgraduate students and undergraduate students. Algebraic geometry. It's a very difficult subject, but the structures that you can come up there are incredibly beautiful. And Gaudí's Sagrada Familia was just a wonderful tapestry of geometrically inspired design.
So could you give some sort of a example of some shape in a different dimension? How could I know it's an impossible task. I'm telling you to do it on an audio, but is there something in your mind right now where?
Well, maybe let's start with something that we can actually visualize. Let's just take a tennis ball, for
Okay.
instance, and just imagine yourself as being an ant just crawling along that tennis ball. How would you see that tennis? If you were the ant, how would you kind of feel like you're walking on that tennis ball? You would kind of feel like you're walking in 2 dimensions, because you can only really walk, around the angle of the compass,
Yeah.
around 360. You can't really go up. You can't really go down. So to the ant, you're just living on a 2-dimensional surface. But for us, we're seeing that tennis ball in 3 dimensions. And in fact, there's some mathematical content there. So the tennis ball is actually a 2-dimensional object, but we just see it in 3 dimensions. Another way to say that is I can describe the surface of a tennis ball just by using 2 dimensions of real space, even though it's in 3 dimensions. The same thing elsewhere. Let's just now describe a 3-dimensional thing and put it in 4 dimensions, and so on and so forth. You can no longer visualize it in 4 dimensions. Well, I can't. Some people can. But that doesn't stop you doing mathematics of higher dimensions just the same way you do the same mathematics in 2 dimensions or 3 dimensions. That's all.
Yeah, no, this is, I think I heard it somewhere that this circle is sphere in, 3 dimension. That's, I think in 3 dimension is sphere the most elegant shape.
Well, elegance is in the eye of the beholder.
That's true.
But so everyone will come up with their own thing. But it is just simply that. Sometimes the job of a mathematics teacher or an educator in any field is to sometimes say to people, sometimes it is that simple. Don't try to complicate things with other things. Just stick to this, and this will get you far enough. That's all that's going on there with a sphere. It's a 2-dimensional thing in a 3-dimensional space.
So I think there's a pretty famous book written by some mathematician about people who were shape of triangles and circles. Somehow, do you know what I'm talking about? It's a book about different dimensions where well, it's not people. I mean, it's that these shapes are alive, and it's a world filled with spheres and triangles, and they have status, and there's a dimensions differences. So, do you know what I'm
No,
no,
I don't know this book,
okay,
sorry.
okay. Yeah, it's somewhat definitely an American mathematician.
Okay.
But I just wanted to throw it in because that's what I just remembered when you were talking about it. Cool. So should we talk about a bit about some other physical aspects like gauge theory or something else? Is there any other concept which you think we can do a little exercise or trying to explain, or maybe some research you are working on? I mean, whatever you feel like would be easier and interesting for you.
I'm not sure. I mean, my research becomes technical and I mean, not too technical for others in my field, but essentially what I'm trying to do is describe. We were talking about these dimensions earlier. Describe these objects that live in higher dimensional spaces by some easier method. I'm trying to describe these geometric surfaces using another tool called combinatorics, which is something you can not easily, but you can program and you can do computations with, and that tells you something about higher geometrical objects. But maybe at this Festival of Mathematics we've had the last 2 days, I quite often get asked by parents and school students, what does research in maths actually do, and where is it going to be used, and is it necessary that students need to know their times tables now because they've all got smartphones and so on, and they've all got phones that can be better at us than chess and everything. And certainly that can be a difficult question to answer. But if there's any merit in the remarks that I have in other colleagues with their remarks as well, is that mathematics literally is everywhere. Number one, it's incredibly useful, but there's something also about pushing the frontiers of human knowledge, which I find very inspiring too. There are problems in mathematics that in my opinion, I think we will never know the answers to. But it is trying to solve these problems and developing the techniques and tools that might make progress on the problem, which shed a lot of light in other neighbouring areas. Maybe there's a date here in mind. There's an example here and a date which is quite telling in my opinion. It only just made this connection the other day. In 1859, Darwin published his Origin of Species. So pulled together all the decades of work he did on species and biological evolution and mutation by random. Well, he didn't use the word mutation, but it's the first time the idea of evolution had really been written down and argued for. And think about how much progress we've made as a scientific community on mapping the human genome, seeing exactly what the tree of life is, seeing exactly how all the species on the planet are related to one another via this tree of life. Also in 1859, a mathematician called Riemann invoked his now famous Riemann hypothesis. Now, what is this hypothesis? It is about the distribution of prime numbers in our number system. So just very quickly, a prime number is something that is just divisible by 1 and itself. 1 and itself.
Yeah.
So 2, 3, 5, 7. You might think 9. 9 is not prime because it's 3 times 3. 11, 13, and so on. These prime numbers there are infinitely many of them. The Greeks knew that. But we don't actually know the distribution of these prime numbers within our number system. And we still don't know that problem, even though it's such an easy problem to state. And Riemann proposed his Riemann hypothesis, which is about its distribution, in 1859. And we still don't know the answer to that question. But that question is one of the millennium problems. It's one of these things that if you solve, you'll earn £1 million. So anyone out there who wants to earn £1 million. But what's also wonderful about that example is it's given birth to so many areas of mathematics on the one hand, but also it's a good thing that problem remains unsolved in a way, because if we did know where the primes were in the number system, then that would break our encryption systems. The whole reason why our encryption systems are safe for the moment is because factorizing numbers into primes and testing whether a number is prime or not is a really hard problem in mathematics. And it's simultaneously a good and bad thing that we don't know what the distribution of primes are. And I like to keep that example because it may seem that biological sciences have moved leaps and bounds, and of course it has, solving many problems. But this problem that's stated in 1859 still hasn't been solved, but it has just made equally the progress in mathematics and the disciplines and sub-disciplines that it's created have just been as equally important, even though the problem still remains unsolved.
No, that is beautiful. I actually understood now that how encryption works. That is fantastic. Actually, I mean, when you're talking about where math is going, and personally, most of the people who have done a lot of math, maybe I'm assuming, but even if you're working on applied mathematics or if you're working on finding out different aspects of physics, you do need maths, if I'm correct. So most of the people who have come back with whatever they have found and have explained it, who are good communicators, actually it has helped me personally to understand where somehow or what is the relationship of my point of view to the world I am at. So it actually allows me to live a bit better, which is a crazy thing to say, but I do think there is a very grounded truth in it, which is that I would be more enlightened, and this is the word I really want to use in that, because it's actually very physical kind of experience which you can measure. You do listen from some of these mathematicians, and then you perceive the universe a bit better, and then you understand your place a bit better, and then whatever boundaries you think you have, or whatever these closets which you might be living in, tends to open up into the bigger ones. And that, I think, is one of the most fundamental, basic joys of being alive. I mean, just to discover that you can live in a very different way. And if I mean, if this could be achieved by, calculating things in that language, I think it's worth it. I mean, what else?
Well, of course, Plato did think in his academy that everyone needed to study mathematics and everyone needed to study geometry, and I think it inscribed on the entrance to the temple, "Let no one who is ignorant of geometry enter here." Well, we don't need to be so strident about these things, but certainly the Greeks thought that the well-lived and the flourishing life must have some training, and a part of this training was mathematics and was geometry, and among many other things. He was very suspicious of poets, so I don't think Paul Keats could help get there. But yes, when you discover these things, or you understand a phenomenon that you previously didn't, it does give you a sense of humility. You are sort of humble before the facts, which is a nice attitude to adopt, particularly in these sort of very strident times. But all those things, but aside from all of those things, it is a great deal of fun to do, and it's a really worthwhile pursuit.
So you must, I mean, you like Dan Dennett, so I'm assuming, and you talked about a lot of philosophers, which means that most of the math or astrophysicists does kind of understand a bit more of a bit more than an average, I don't think, like average population about philosophy, and they do engage a little bit. And I think now philosophers are trying to come back to the picture and pose problems where there is a role for philosophy. But I could see that you have also been engaging with that. So how much you think on a philosophical problems which is informed by your mathematical training?
Well, maybe perhaps pure mathematics or pure mathematicians might have a bit more of an overlap with some philosophy, because of course, I mean, back in ancient Greece, everything was the same. And in fact, it's very nice to be in the faculty of the liberal arts, because in the old traditional sense of the term liberal, it encompassed history, art, literature, mathematics. All these things were in the same region, which is a good thing, and I think we shouldn't lose sight of that. And of course, STEM is important. STEM subjects are hugely important, but also the arts is incredibly important for asking the question of who we are and how we want to live. So I don't want to diminish those subjects either, but in terms of philosophical questions, well, there are certainly some great questions and some serious questions that need to be asked about the role of artificial intelligence in the ways we do things. To what extent we'll allow ourselves to be governed by algorithms or manipulated by algorithms, and so on and so forth. So policymakers need to be aware of this. Mathematicians also need to be aware of this. So there's a great conversation that needs to be had that involves mathematicians, philosophers, writers, social scientists. So to the extent that we should be sharing our knowledge and participating in a wider conversation about how our disciplines can contribute to the wider society.
So I'm assuming now that you must have thought a bit about free will. Have you? Yeah, I know. Just because you're mentioning Daniel Dennett and also certain aspects, have you thought about what do you kind of think of free will? And this is your opinion, of course. We know it. Have you, or am I just?
Well, that's a really difficult one to end on the podcast.
That's true.
Well, maybe we can keep going. Free will. That's a tough one. Mm-hmm. Well, maybe I'll peel it back to mathematics as well. The good thing about having a fluency and a competency in mathematics is it does allow you to poke your nose into other areas too, and allows you to understand things that you might not be able to previously understand, particularly if they're going to be if complexity theory is going to come in, or some technical details that need calculation need to come in. On the topic of free will, I remember a few years ago, and maybe they're still out there, that there were these experiments where they hook an MRI machine to your head, and they ask you to press a left button or a right button, and I don't remember the results correctly, but the idea was that the scientists could tell which button you're going to press before you were conscious of which button you're going to press, and so on and so forth. And some took that to be, well, that we don't have any free will. We don't have any free will. We can just see what you're going to do. And I hadn't really read the literature on it, but my reaction was, that experiment doesn't show you that you don't have free will. That shows you that you're not a random number generator.
Yeah, exactly.
Right? That shows you're not a random number generator. Now, of course, anyone who wants to do free will can go and read the numerous books on that philosophers have written, and of course, Dennett is one. But I really like his view that free will should be a kind of competence. It is a kind of competence, and when we think about free will, we're asking not the right questions. We're asking whether someone knew in advance whether you're going to do something, or whether you could have done otherwise. Then it turns that around and shows in one of his books that free will is a thing that has evolved gradually, that evolution, that biology is the place to be looking for free will, not physics. The Heisenberg uncertainty principle won't give you free will, but biological evolution, creating structures that are more complex and able to do more things or better things, that is the degrees, the increasing degrees of freedom of free will, and well, that's as much as I want to dip my oar into it.
No,
but it's a really fascinating topic.
I mean, I think it's very interesting coming from you, especially because it's hard to talk about free will with generally, but I think because you're solving difficult question, you are comfortable tapping into this. So it is very good that I heard that, because I think when someone asks or I listen about free will, I think biggest problem is the definition of free will, where they consider to have a control over an environment, which then is you being part of evolution, and then the cosmos, and then all the rules and what we kind of know, and so much we don't know, and everything kind of get muddled up, and then the free will comes like either we have it or we do not have it. And I think this is a very beautiful point where biology actually kind of allowing you on that level where there is meaning and culture.
Well, think about on the topic of degrees of freedom. Just think about you're trying to build a computer that is playing chess, for instance. You're trying to build a computer program that's playing chess, and you might have a computer that is more powerful than computer B, might be more powerful than computer A, and there are greater possibilities available and be able to be computed in computer B that provides it to be a superior player to computer A. That's the kind of degrees of competence that we're talking about here. What are the specs of free will? There are various varieties of free will that we don't have, and that subtracts nothing from our responsibilities to one another, how our laws will govern our societies. We can still have all the responsibility that this whatever definition of free will that comes from the biological evolution gives us. We can still create our societies just the same as we did with the old versions of free will.
Definitely. So just in the last, is there any interesting universal phenomena which you think is mostly explored by mathematics, and generally when you think about it, it doesn't really make sense? Would you like to give something about that through I mean I don't know, black holes, sun, how suns stars are working, something like that, or even your surface?
No, I think I think what's so wonderful about mathematics, and just to return to our discussion about getting over our poorly evolved intuitions, is it allows you to be surprised by how bad our intuitions can be sometimes. Here's a nice little problem that I'll leave with the listeners. And it's called the birthday paradox. So if you want to cheat, you can Google it online. But the problem is this: how many people in a room do you need before the probability that two people share the same birthday is around a half?
54. No.
You think, oh golly, well, there's 365 days in the year. Well, the probability that we share the same birthday is pretty low, and then we'll bring in another person. We don't share the same birthday. You think you'll need a great number of people. The answer is, I think, is about 26.
Oh wow!
So the probability that half you have 26 people in a room, you have a probability of around about a half that two people will share the same birthday.
Okay, so 50% probability.
Around probably, yeah,
okay,
50%.
So yeah. Wow.
And I remember seeing that in high school, and I just couldn't believe it. And when you do the calculation, you think it works. It really works.
Wow.
And so maybe this is another plug for the discipline of statistics as well. Statistics really does allow you to get to the essence of a problem and pick out bits that are important. And even though I'm not a statistician, if I'm giving a talk to some high school students or even some first year students, I'll quite often go to these kind of statistical, almost / psychological problems of psychology to show us how useful this sort of mathematical and statistical thinking can be in helping citizens be responsible and informed and reflective as they go about their lives.
Perfect. Is there anything else you'd like to add?
No, I've enjoyed the questions.
Brilliant. I mean, thanks a lot, Neil, for sure illuminating a lot of topics about math and, allowing me to finally dip a little bit into this language and talk to someone. And maybe I hope that most of the listeners might have picked up something about math, which they would like to explore further. But thanks a lot.